Welcome to Chapter 13 of the AEON-CASIMIR Dossier. In this chapter, we move beyond perception and delve into the sophisticated world of communication, signaling, and synchronization within relativistic and curved metric domains. As we explore the AEON LCV, Omega-1 craft's unique environment, you'll discover how information is exchanged and preserved when classical electromagnetic signaling becomes unreliable, time dilation varies across the vehicle, and external reference frames are distorted or disconnected. This chapter is designed to provide conceptual clarity, explicit mathematical grounding, and a strong foundation in signal theory, setting the stage for a deep dive into the layered architecture that enables communication in the most extreme environments. The objective of this chapter is to define how information is transmitted, synchronized, and preserved under challenging conditions. These include unreliable classical electromagnetic signaling, varying time dilation across the craft, operation within engineered spacetime curvature, and the distortion or disconnection of external reference frames. The AEON LCV, Omega-1, does not depend on a single communication paradigm. Instead, it employs a robust, layered signaling architecture that ensures reliable information exchange in even the most extreme and relativistic environments. In curved spacetime, simultaneity is not absolute. This fundamental constraint means that clock synchronization and information exchange must be covariant remaining invariant under coordinate transformations. The AEON-CASIMIR communication systems are designed to be metric-aware, ensuring that information is preserved and meaningful regardless of the observer's frame of reference. This approach moves beyond simple timestamps, embedding the geometry of spacetime directly into the communication protocol. Metric-aware signaling is at the core of AEON-CASIMIR's communication strategy. Rather than relying on raw timestamps, the system encodes information in a way that remains consistent across different frames of reference. This ensures that even as the craft moves through regions of varying spacetime curvature, the integrity and meaning of the transmitted information are preserved. Such a system is essential for navigation, coordination, and operational safety in relativistic environments. The baseline layer of the AEON LCV, Omega-1's communication system retains standard radio frequency, microwave, optical, and laser systems. These are used for line-of-sight operations, compatibility with external infrastructure, and as a fallback. However, electromagnetic propagation is continuously corrected for local spacetime curvature. The wave vector is dynamically adjusted, ensuring that signals remain accurate and reliable even as the craft traverses regions of varying geometry. To maintain signal integrity, the AEON LCV, Omega-1, applies mathematical corrections to electromagnetic propagation. The phase shift is calculated as the integral of the wave vector over the path, with the wave vector dynamically adjusted for local curvature. This ensures that the signal's phase and timing remain accurate, compensating for the distortions introduced by the craft's relativistic environment. Such corrections are vital for maintaining communication reliability. Surrounding the AEON LCV, Omega-1 are plasma rings that act as advanced waveguides. These channels enable the craft to steer signals, shield transmissions, and encode information into various plasma modes. By modulating the electron density within the plasma, the craft can achieve highly directional, low-leakage communication. This approach not only enhances security but also allows for efficient information transfer even in challenging environments. Signal propagation through plasma channels follows the plasma dispersion relation. The frequency squared equals the plasma frequency squared plus the speed of light squared times the wave number squared. By adjusting the electron density, the plasma frequency can be controlled, allowing the craft to steer and encode signals with precision. This mathematical foundation is key to understanding how plasma-guided channels operate. By leveraging the properties of plasma, the AEON LCV, Omega-1 can achieve highly directional communication. Signals can be steered with precision, minimizing leakage and enhancing security. This method allows the craft to maintain robust communication links even when traditional electromagnetic channels are compromised or unavailable. Beyond plasma and electromagnetic channels, the AEON LCV, Omega-1, can encode information directly into spacetime curvature. These micrometric fluctuations propagate differently than electromagnetic waves and can be detected by specialized sensors. This approach enables communication through regions that are opaque to traditional signals, expanding the craft's operational envelope. Specialized sensors, such as spacetime gradient sensors and CASIMIR boundary detectors, are used to detect the subtle fluctuations in spacetime curvature that carry encoded information. These devices are finely tuned to pick up on the micrometric signals, allowing the craft to receive communications even in environments where electromagnetic waves cannot penetrate. CASIMIR cavities within the craft possess quantized vacuum energy levels. By making small changes in the boundary separation, detectable shifts in energy occur. Information is encoded by modulating these vacuum energy states, creating a passive, low-energy, and highly resistant channel for communication. This method is particularly effective for stealthy and jam-resistant signaling. The CASIMIR effect is described by the quantized energy levels within a cavity. The energy is inversely proportional to the cube of the boundary separation. By modulating this separation, the craft can encode information into the vacuum state. This mathematical relationship underpins the craft's ability to use vacuum energy as a signaling channel. Vacuum state signaling offers several advantages. It requires extremely low energy, is passively detectable, and is highly resistant to jamming. These features make it an ideal channel for secure and stealthy communication, especially in environments where traditional methods are vulnerable to interference or detection. To maintain internal coherence, the AEON-CASIMIR system uses entangled quantum clock references. Entangled states allow phase correlation to persist regardless of spatial separation, enabling the craft to correct clock drift, align frames, and ensure temporal coherence. Importantly, this method does not transmit information faster than light. It only maintains correlation, preserving causality. Quantum entanglement enables the AEON LCV, Omega-1, to synchronize its internal clocks with remarkable precision. The entangled state ensures that any phase drift is immediately corrected, keeping the entire system in temporal alignment. This is crucial for operations that demand exact timing, such as navigation and formation flying. Within the AEON LCV, Omega-1, two simultaneous time domains are managed: internal proper time and external coordinate time. A mapping function relates these domains, ensuring that communication packets include metric metadata. This preserves the meaning of information as it moves between different frames, maintaining coherence and operational integrity. The mapping between internal proper time and external coordinate time is mathematically defined. The integral of the square root of the metric components and velocity terms ensures that the relationship between time domains is accurately maintained. This mathematical rigor is essential for preserving the integrity of communication across different frames. Communication systems aboard the AEON LCV, Omega-1, must contend with noise sources such as plasma turbulence, vacuum fluctuations, and relativistic drift. These are mitigated through active stabilization of coherence length, using plasma feedback and CASIMIR tuning. By continuously monitoring and adjusting system parameters, the craft maintains reliable communication even in the presence of significant disturbances. The coherence length is inversely proportional to the change in the metric tensor. By minimizing these changes, the system maximizes coherence and suppresses errors. This mathematical relationship guides the active stabilization strategies employed by the AEON LCV, Omega-1, ensuring that communication remains robust even under dynamic conditions. Low observability is a priority for the AEON-CASIMIR communication system. Directional plasma confinement, non-emissive vacuum signaling, and metric-encoded transmission methods ensure that external observers cannot detect conventional broadcast signatures. This stealthy approach protects the craft from unwanted attention and interference. By combining multiple stealth techniques, the AEON LCV, Omega-1, ensures that its communication remains undetectable. These include tightly confined plasma channels, vacuum state signaling that emits no conventional energy, and encoding information into spacetime metrics. Together, these methods provide a comprehensive shield against detection. In the AEON-CASIMIR system, communication is not just for data exchange. Signals are integral to frame stabilization, relative positioning, and formation coordination. This tight integration means that communication and navigation are mathematically inseparable, ensuring precise control and alignment during complex maneuvers. The mathematical models used for communication are deeply intertwined with those for navigation. By embedding navigation data within communication signals, the AEON LCV Omega-1 ensures that all systems remain synchronized and coordinated. This integration is essential for maintaining formation and executing complex flight paths. When faced with decoherence, metric instability, or external interference, the AEON LCV Omega-1 transitions to isolation protocols. These include local-only synchronization, internal closed-loop timing, and autonomous operation. Such measures ensure that the craft remains operational and coherent even when external communication is compromised. During isolation, the AEON LCV Omega-1 relies on its internal systems for synchronization and timing. Closed-loop protocols maintain coherence, allowing the craft to operate autonomously until external conditions stabilize. This resilience is critical for mission success in unpredictable environments. Operators interact with the AEON LCV Omega-1's communication system through intuitive interfaces. These include stability indicators, latency maps, and coherence meters. The complexity of raw tensors and quantum states is managed by AI, allowing human operators to focus on mission objectives without being overwhelmed by technical details. Artificial intelligence plays a central role in managing the AEON LCV Omega-1's communication systems. By interpreting raw data and presenting it in user-friendly formats, AI ensures that operators have access to actionable information without needing to understand the underlying mathematics or quantum mechanics. Chapter 13 establishes several key principles for communication in curved spacetime. Communication must be metric-aware. Plasma and vacuum states serve as signal carriers. Synchronization relies on correlation rather than simultaneity, and information survives relativistic distortion through geometric encoding. These principles form the foundation of the AEON-CASIMIR communication architecture. Metric-aware communication ensures that information remains meaningful and intact across different frames of reference. By embedding spacetime geometry into the signaling process, the AEON LCV Omega-1 overcomes the challenges posed by relativistic environments, maintaining operational coherence and safety. Utilizing plasma and vacuum states as signal carriers allows the AEON LCV Omega-1 to communicate in environments where traditional methods fail. These channels provide flexibility, security, and resilience, ensuring that information can always find a path to its destination. Synchronization within the AEON-CASIMIR system is achieved through correlation, not simultaneity. By maintaining phase relationships and entanglement, the craft ensures that all systems remain aligned, even when absolute simultaneity is impossible due to relativistic effects. Through geometric encoding and metric-aware signaling, information survives the distortions of relativistic environments. The AEON LCV Omega-1's communication system is designed to adapt to changing conditions, ensuring that data remains accurate and actionable no matter how extreme the environment. A key insight from Chapter 13 is that the AEON-CASIMIR system does not transmit messages in the conventional sense. Instead, it aligns reference frames across reality, ensuring that all parties share a common understanding of information, regardless of their position or motion. Aligning reference frames is central to the AEON-CASIMIR communication philosophy. By ensuring that all observers interpret information consistently, the system overcomes the ambiguities introduced by relativistic effects and curved spacetime. The operational implications of this communication architecture are profound. By integrating communication, navigation, and synchronization, the AEON LCV Omega-1 achieves a level of coherence and control that is unmatched in conventional systems. This enables new possibilities for exploration, coordination, and mission success. Looking ahead, the principles established in Chapter 13 pave the way for even more advanced communication systems. As our understanding of spacetime and quantum mechanics deepens, new methods for information exchange and synchronization will continue to emerge, pushing the boundaries of what is possible. Throughout this chapter, several key equations have been introduced. These include the metric tensor for clock synchronization, plasma dispersion relations, Casimir energy formulas, and coherence length expressions. Each equation plays a vital role in the design and operation of the AEON-CASIMIR communication system. The communication systems described in Chapter 13 are deeply integrated with the AEON-CASIMIR field architecture. This integration ensures that all aspects of the craft's operation, from propulsion to navigation, benefit from the advanced signaling and synchronization methods developed here. Advanced communication and synchronization are essential for the AEON LCV, Omega-1's propulsion physics. By maintaining precise alignment and coherence, the craft can execute complex maneuvers and operate safely within engineered spacetime environments. The control and field architecture of the AEON LCV Omega-1 relies on the robust communication systems outlined in this chapter. By ensuring that all subsystems are synchronized and aligned, the craft achieves a level of operational harmony that is critical for mission success. In summary, Chapter 13 of the AEON-CASIMIR Dossier provides a comprehensive framework for communication, signaling, and synchronization in relativistic and curved metric domains. By combining advanced mathematics, layered architectures, and innovative signaling methods, the AEON LCV Omega-1 sets a new standard for information exchange in extreme environments. The innovations described in this chapter highlight the importance of adapting communication systems to the realities of relativistic travel and engineered spacetime. As technology advances, the principles established here will continue to guide the development of even more resilient and capable systems, ensuring that information remains the lifeblood of exploration and discovery. With Chapter 13 now complete, the AEON-CASIMIR Dossier stands as a testament to the power of innovation in the face of unprecedented challenges. The communication systems developed here not only enable survival in the harshest environments, but also open new frontiers for exploration, understanding, and human achievement.